This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is gas compressibility factor. Given nitrogen at 20 bar and minus 100 C, what's the compressibility factor, Z? And what's the specific volume at this state? All right, we're going to use the compressibility factor. So we're told to do that. There's a chart for that. Z is a function of PR and TR, where these are reduced pressure, reduced temperature, and these are pressures and temperatures made dimensionless by the critical point. So the first thing we need is a critical point, and we have a table for that. Let's go find the table to find the critical point. It's this one. This happens to be table A1 on molar mass and critical point properties. From a particular name of the table and page number of the table, we're going to use that. These are alphabetical. Here's nitrogen. So critical data is over here. On the right-hand columns, we've got temperature in kelvins and pressure in megapascals. So let's transfer that to the other document. Jot that down. First of all, I'm using table A1, page 910, and then you'd need to state if whatever I'm doing this as an example, tell me what book you're using. The data we got was the critical temperature was 126 kelvins. The critical pressure was 3.39 megapascals. Let me convert that to bar. That's going to be 33.9 bar. I'll say recall that 1 bar is 10 to the 5th pascals. And of course a megapascal is 10 to the 6th, so that's the conversion there. Oh, one other piece of data I'm going to need later is that on that table was the molecular weight. Molecular weight is 28.01 kilograms per kilomole. That's for nitrogen. All right. Given that information, let's compute now the reduced pressure and reduced temperature. PR is going to be the given pressure, 20 bar, divided by the critical point, 33.9 bar. And that gives me 0.5899. That's a dimensionless quantity. And the reduced temperature is going to be, I need, because this value is in Kelvin, I need the state I'm given in Kelvin. That's going to be 273 minus 100, that'd be in Kelvin, divided by 126 Kelvin, and that's about 1.37. Okay, now we're going to use a compressibility chart. Before I write that, before we go to the chart, I'm going to say we're going to use the chart. We're going in at PR at 0.59, and we're going in at TR, let's say 1.4. We'll round that off. Let's go find a chart and look at that. Nope, wrong direction. Here we are. Here's a compressibility chart. And the Z factor over here is the vertical axis, and the reduced pressure is the other axis. And then there's lines of different values of the reduced temperature. And here is 1.1, 1.2, 1.3, 1.4. That's the one we want. So we want to follow along this line of 1.4, which goes like this. And we want to come in at 0.59, which is here. So 0.59 comes up this way. 1.4 comes across this. Now stop that. Actually, that'll work. 1.4 comes across this way. So the point we want is this value. This line is 0.9, 0.91, 2, 3. Looks like about 0.935. And you can see over here 0.9. So I'm going to pull off the value of 0.935 from this plot, where these two lines cross, and I have to pick off a value off of this axis. Let's go back to the other document and transfer that. So I'm going to find that these two input values of 0.59 reduced pressure, 1.4 reduced temperature, gives me Z of about 0.935. Now, it would be perfectly acceptable to stick to 2 digits. Because it's hard to read more than about 2 digits off of a chart. All right, so that's responsive to part A. I'm asked to find the compressibility factor. There it is. Part B says, given the compressibility factor, what's the specific volume? Well, the compressibility factor is defined to be pressure times the molar specific volume divided by the universal gas constant divided by the temperature, absolute. And I'm going to use, I'll say recall, that the molar specific volume is the same as the ordinary specific volume times the molecular weight, where V bar is meters cubed per kilomole, and V is meters cubed per kilogram, and capital M molecular weight is kilograms per kilomole. So that's the conversion there. So we can make this conversion here, and then I'm going to take this bit here, and I'm going to solve for Z. Solve for V. And V, solving for this guy, turns out to be Z times R bar times T divided by pressure divided by molecular weight. And now I've got a path for putting in some numbers. All right, what are my numbers? Z I found from part A is 0.935. The universal gas constant I'm going to put in as 8.314. Temperature has got to be the temperature I'm interested in kelvins, 273 minus 100. That's got to be an absolute temperature. Pressure, I'm going to put in as pascals, 20 times 10 to the 5th. And then molecular weight is 28.01. Let's check the units on that. I've got the universal gas constant is kilojoules per kilomole per Kelvin. And then I've got kelvins. And then pressure in pascals is newtons per meters squared. And then molecular weight is kilograms per kilogram mole. Moles drop out. Kelvins drop out. Kilograms remain, that's good. I've got kilonewtons and I've got newtons. To make that fix, I'm going to add a conversion. I'm going to take 1,000 joules, which is a Newton meter, per 1 kilojoule. So this is a conversion here, and that gets rid of kilojoules, that gets rid of newtons and newtons, and I have left meters cubed per kilogram. That's my units, work out okay. Let's crunch the numbers. V is going to be 0.02401 meters cubed per kilogram. That's what I was asked to find. All right. Suppose instead of using the compressibility factor, we had used the ideal gas law. What would have been the error? The ideal gas law would have been 1 equal P V bar over R bar T. That is to say, Z equals a 1. So my error here would be, my error on volume would be the same as the error on Z. So the right value was 0.935. Oops, 0.935 the error value, the wrong error was 1, and the correct value was 0.935 times 100%. That gives 6.9%. So if I had used the ideal gas situation at this point, it'd be off by a little bit, 6 or 7%. All right, can we recap? When you're asked to find a compressibility factor, you use the chart. It turns out that it's important when the state you're interested in this case high pressure and low temperature, is close to the critical point. And the critical point for nitrogen is 126 Kelvin and about 30 some atmospheres. So high pressure, low temperature, we have to worry about compressibility factor. When you use a chart like this, say which chart, what values you use going in, and then what values you got coming out. So that'll make it possible for somebody to follow your work. And then whenever you do something related to compressibility or the gas law, make sure you use absolute temperature. And if you use absolute temperature, then all will be well.